Okay, so let's work through basic definition of a logarithm and how to evaluate them, some basic properties of logarithms, and how we use that to both expand and condense a logarithm. So basically, you always want to think of a logarithm as an exponent because your brain works better with exponents at this point. So when you see a logarithmic statement, you want to get used to thinking about it in terms of exponents instead, and that should help you. So our basic definition, a log to any base of a number is equal to some value. If and only if, that means it goes both ways, if that same base raised to the value is equal to the number. Now, what's important too is for a logarithm, the base has to be greater than 0. So that means it can't be 0 and it can't be negative. It also cannot equal 1. Okay, so again, the base has to be positive and it cannot be 1. And the number next to the logarithm also must be positive. Okay, so no negatives over here. In addition, the base cannot be equal to 1. All right, so here's how you go back and forth. You have 2 cubed equals 8. The base is 2 raised to a power of 3, and it equals some number 8. The logarithmic form of that would be log base 2. So again, the base of the exponent is the base of the log. Log base 2 of 8 equals 3. So the way I like to think about it is the base of the exponent should also be the base of the log. And then you have these other two numbers, and they're going to swap places. Okay, so the 3's on the left and the 8's on the right over here. And over here, it's the opposite, 8 on the left, 3 on the right. So if we were to do a couple of examples, say 2 to the 5th equals 32. That would be if and only if log, the base of the exponent is 2. So we're going to have the base of the log be 2. And then the 5 and the 32 are going to swap sides. So I'm going to put 32 on the left and 5 on the right. So 2 to the 5th equals 32. If and only if log base 2 of 32 equals 5. Let's see, 4 cubed equals 64. If and only if log, base of the exponent is the base of the log, the other two numbers switch sides. Log base 4 of 64 equals 3. Okay. So you want to be able to go back and forth between exponential form and logarithmic form. So when it says to evaluate a logarithm, basically you could set it equal to x and then you're kind of solving, but you want to think about it in its exponential form. So let's say we make this equal to some x value that we're trying to find. Okay, so it's not really an equation because we're just evaluating, but we're going to pretend because we're trying to figure out what log base 2 of 16's value is. So the exponential form of this would be 2 to the x equals 16. Well, what power of 2 equals 16? 2 to the 4th equals 16. Therefore, the answer is 4. So log base 2 of 16 equals 4. So if we do that same thing here, 3 to what power equals 27? Well, 3 cubed is equal to 27. So this must equal 3. You don't always have to write it out. If you get good at it, you can kind of do it in your head. The exponential form here would be 5 to what power equals 1? Well, anything to the 0 power equals 1. So it evaluates to 0. So here, let's say we just think about it in our heads. It would be 4 to what power equals 16? Well, 4 squared equals 16, so the answer is 2. 4 to what power equals 16? This would be 2 to what power equals 32. I use that as an example up here. 2 to what power equals 32? 2 to the 5th power. Next up, we have some properties of logarithms. And want to remember some basic rules that were mentioned earlier. The base of the log has to be positive. It can also not equal 1. And any value next to the log has to be positive. Okay, so when you look at properties of logarithms, there is a way to condense it, and then there's a way to expand it. So the first property would be a log to some base of a product, a times c, can be expanded to log of that same base of a plus log of that same base to c. So the product AC was split up into separate logarithms, all using the same base. So as an example, let's say I had log base 4 of 3x. I could expand that into log base 4 of 3 plus log base 4 of x. The next property, a log to some base of a quotient can be expanded to log with the same base of the numerator minus log to the same base of the denominator. So this quotient was split up into separate logs with subtraction. So let's say I had log base 5 of x divided by y. I could expand that to log base 5 of x minus log base 5 of y. Next, we have a property that says a log to some base of some value raised to an exponent. That's the condensed version. We can expand that by moving that exponent out front to be a coefficient. And that would be the expanded version. So you have a logarithm raised to an exponent. You can expand it by taking that exponent and rewriting it as a coefficient. So let's say I had log base 2 of x to the 4th. That could be rewritten as 4 log base 2 of x, just moving the exponent out front. Some other properties, kind of think of these as shortcuts. Anytime the base of the exponent matches the base of the log, they cancel each other out. It's like squaring a square root. They undo each other because exponents and logarithms are inverses. So if the base of the exponent matches the base of the log, they just undo each other and you're left with whatever else is sitting there. So if I had 3 raised to the log base 3 of x, my answer would just be that x because the base of this exponent matches the base of that log. Okay. Anytime the base of the exponent matches the number next to it, it's just going to equal 1 because in exponential form, it would be b to what power equals itself. Well, anything to the first power equals itself. So as an example, if I had log base 2 of 2, that automatically is going to be equal to 1, or log base x of x is equal to 1. If the base of the log matches the value next to it, it always equals 1. For number 6, log to any base of 1 will always equal 0, because think about the exponential form, b to the 0 power equals 1. Anything in the 0 power equals 1. We saw that up here with example 3. So if I have log base 7 of 1, it equals 0. Log base 9 of 1, it equals 0. Log base x of 1, 0. And then the property right here kind of goes along with the one in number 4 because the base of the log matches the base of the exponent. We saw that here, the base of the exponent matched the base of the log. We've just reversed the order. The base of the log matches the base of the exponent, so they just cancel each other out and you're left with that p-value. So if you had log base 4 of 4 to the 7th power, then my answer would just be 7. Okay, so some of the practice problems let's look at. We want to be able to write in exponential form. So again, if you want to pause the video and work through some of these and then come back to check your work, you can. Express in exponential form. So the base of the log will also be the base of the exponent, and then the 64 and 3 will swap sides, so it'll be 4 cubed equals 64. Next example, express in log form. So using that same rule, the base of the exponent should be the base of the log, and the other two values swap places. So log base 2 of 1/8 equals -3. Okay, now we're going to use some of those properties to expand and then condense. So if you look at the rules that we went over, the left side is the condensed version and the right side is the expanded version. So right here, if we're trying to expand, expanding uses addition, subtraction, and coefficients. So we want to change multiplication into addition, division into subtraction, and exponents into coefficients. Then it will be expanded. So right here we have a single logarithm. Condensed version is always a single logarithm. So, and we've got a product with also an exponent on the y. So the product will be split up into separate logs with addition, and then we will need to make this exponent be a coefficient. So log of x plus log of y squared. But we're not finished because we need to have coefficients instead of exponents. So our final answer would be log of x plus 2 log y. Now you may have noticed there's no base written on this log. So there are two commonly used logs, and when you don't see the base written, that's literally referred to as the common log, and it's understood that the base is 10. It's kind of like if you see a radical, like this right here, we understand that that's a square root. There doesn't need to be a little 2 written as an index. We just know that's a square root. If it weren't, we would see the index written. So if it were a cube root, then I know that I would see that index written. So we understand that if we see a log with no base, that is the common log and it's base 10. So if you look at your calculator down the left-hand side, here is the log button, and that represents log base 10. And underneath it is the other commonly used logarithm, which is called the natural log, and that is log base e. We'll go into more detail about e later, but it is like pi. It's an irrational number. We use 2.718, just like we use 3.14 for the rounded version of pi. And it is a value that was discovered to appear with exponential functions and logarithmic relationships. Okay, so go back to our notes. So here we have a couple things. We have a quotient, and then we have a square root on our x and an exponent on our y. Well, nowhere in our properties do we have anything about radicals, but we have learned earlier in the year how to rewrite radicals as exponents. So I'm going to change this to x to the 1/2 over y squared, because I do have properties that tell me what to do with exponents, but I don't have any properties that tell me what to do with radicals. So I'm going to split the quotient into separate logs subtracted. So log of the numerator minus log of the denominator. But I'm not finished, because if you're expanding, exponents need to be written as coefficients. So 1/2 log x minus 2 log y. And that would be my final expanded version. If you're condensing, you're going the opposite way. So we want to end up with just one single logarithm, and we want to use multiplication, division, and exponents. So the addition will change to multiplication, the subtraction will change to division, and coefficients will change to exponents. Okay, so again, only one logarithm when you're finished, and that's a common error, especially if there's a fraction. A lot of students will put a log in the numerator and a log in the denominator, but there should only ever be one log. So the first thing I'm going to do is take this coefficient and rewrite it as an exponent. And now I have 2 logs subtracted, so that should be rewritten as 1 log divided, so 9 to the 1/2 is going to be the numerator and 4 will be the denominator. Now you actually should simplify a little bit further because 9 to the 1/2 power means the square root of 9, and we all know that the square root of 9 is 3. So this really should be most simply written as log to the 3/4 power. All right, number 2 is kind of a brain teaser. It uses some of those properties though. So remember from your properties that if the base of the exponent matches the base of the log, they cancel each other out. And remember that if you don't see the base written on a log, it's because it's called a common log and it's 10. So the base of the exponent does in fact match the base of the log and they cancel out and you just have 2. The rest of it's a bit more complicated. You basically have to use your exponent rules, but in reverse, which is not something that you usually would do. So we have rule in exponent that says if the bases are the same and we're multiplying, we add exponents. Well, it looked like something's been added in this exponent. So I'm going to reverse that rule. Instead of if the bases are the same and you're multiplying, we add exponents. I'm going to rewrite that as the bases are the same and we are multiplying. Instead of having the exponent where we've already added. So here's how the rule would be applied. Bases are the same, we're multiplying, we can add these exponents, which is how we would be able to get it written in this way. So then we can continue to simplify. Obviously, 10 squared is 100. Okay, so right here, we have a log with a coefficient. So what I want to do is I want to use one of my properties and I want to condense this logarithm by moving that coefficient to be an exponent. So I'm going to rewrite just that logarithm as log of 5 squared. When I do that, I now can apply the property where the base of the exponent matches the base of the log. They have to be right next to each other, which is why I needed to move that 2. So now the base of the exponent and the log are right next to each other and they have the same base. So they're going to cancel each other out and I'm just going to be left with the 5 squared. And now it's just straight computation. 2 plus 100 times 25, 2 plus 2,500. So my answer is 2,502. All right, so the last part of these notes, your change of base formula. So why do we need a change of base formula? Well, as I showed you before, our calculator does have a common log button and a natural log button. Okay, these buttons can be found on pretty much any scientific calculator. So we always should have on any scientific calculator a common log and a natural log. And so what if I have a log of some other base that I would like to calculate? Well, the change of base formula is how you can use the common log or the natural log to calculate the value of a log that has some other base. So as this says, you have a log to some base of a number. Well, as long as the bases of these two logs are the same, whether it's common log or natural log or really any base, but we want to use the buttons on the calculator, then we can get an equivalency and we can use a calculator to get the value. So I'm going to take log base b of n and I'm going to change it to common log of n divided by the common log of the base. So it's always going to be the number over the base, just using the common log. Or if I prefer, log base b of n could be converted to natural log of n divided by natural log of b. So that would allow me to use either one of those buttons on the calculator. So, for example, let's say I wanted to find log base 3 of 7. Well, on my calculator, I could either do common log of 7 divided by common log of 3, or natural log of 7 divided by natural log of 3. So let's do that. Okay, so I'm going to set up a fraction. And the common log of the number divided by the common log of the base. Hit enter, and that says that's the value. That should be the same as the value of log base 3 of 7. I could also do natural log of 7 divided by the natural log of 3. Again, as long as the two bases on the logs from your numerator and denominator are the same, it would work, but you can't use just any base on your calculator. And you get the same answer. Now, that's not exactly true if you have certain calculators like this one, because on this calculator, you have the option of choosing alpha, window, and choice number 5 is log base. And if I have that option on my calculator, I can actually type in log base 3 of 7, and I don't have to use the change of base formula. But again, that's not an option on every calculator, and that's why the change of base formula exists. But now you can see that that gives you the same answer. Okay, one other topic to talk about is the natural base e. Okay, so I mentioned this earlier. It is the base to a natural log. So log base e is written as natural log. Okay, where we don't write the base. When we see that ln, we know it means log base e. It's not a variable, even though it's a letter. It's like pi. There is e button in your calculator in 2 different places. The second natural log gives you e to some power. And you also have second divided by, and you just get e, and you can do whatever you want with it. If I just hit enter here, you can see it is an irrational number, so it keeps on going forever with no repeat. It's non-terminating, non-repeating, but we use 2.718, just like if we chose pi, it is also irrational, but we use 3.14. Okay, so basically logarithms and the value of e shows up a lot with exponential growth and decay and logistic growth. And probably the most popular application when you are investing or borrowing money oftentimes is calculated with something called continuous compounding formula. And that formula for continuous compounding is the amount is equal to the original amount invested or borrowed times e raised to the rate times time. And that formula uses the, it's called Euler's number, e. Okay, so you have in your module, you have practice with some answers, and then there is the assignment that is due at the end of the week.